Welcome students. Today we are going to discuss about the important topic Maxwell's equations. So Maxwell derived the four equations from the fundamentals law of electromagnetics. So that is called as Maxwell's equation. First we can see Maxwell's equation from Ampere's circuit law. So according to Ampere's law we can state that the line integral of magnetic field intensity H on any closed path is equal to the total current enclosed. That is line integral of H dot dl is equal to I. Again I value we can write closed surface integral of current density into area. So the total current involves the current is the both conduction current as well as displacement current. So conductive current is the current in the resistive element and displacement current is the current in the capacitive element. So according to our Max definition, we can derive conduction current density Jc. So here two currents we derived Jc and another one is Jd, that is the displacement current. So current flow through resistive element is conductive current and the current through capacitive element is displacement current. So according to Ohm's law, we can easily find out what is the value of current in the resistive element. IC equal to V by R. Again the formula for R is equal to R is directly proportional to N and inversely proportional to area. That proportional constant you are usually say resistivity. So it is depending upon the type of material. So rho into L by A. Again 1 by rho is the conductivity of the material. So replace with conductivity. So L by sigma into A. So therefore IC value we can write V into sigma A by L. Suppose if E is the electric field, then the voltage V is equal to E into I. So here I is defined for conductive current, conductivity current. So IC is equal to E into sigma A. Therefore IC by A is equal to sigma into A. Therefore conduction current density J, the current density is equal to current per unit area. So you can write JC is equal to IC divided by A. So JC is equal to sigma into E. Similarly, displacement current density ID equal to, so I is equal to the current flow through capacitor is equal to dq by dt, rate of change of current. So dq by dt, again the value of capacitance C is equal to q by V. From this we can write total charge q is equal to C into V. So ID is equal to C into dV by dt. So the capacitance of a parallel plate capacitor, already we derived the derivation C is equal to epsilon naught A by D farads. So where epsilon is the permittivity, A is the area of cross section of the plate, D is the separation of plate. Therefore ID equal to epsilon A D by dV by dt. Substitute C value in ID. Again we know V is equal to E into D. Now substitute the value of ID here. So ID is equal to epsilon A by D into D. So instead of V, substitute E into D. So D is a constant. So dE by dt. Therefore ID equal to epsilon A into dE by dt. So ID current density is equal to current per area. So ID by A is equal to epsilon into dou E by dou T. So we know electric flux density D is equal to epsilon into E. So replace that one. Therefore displacement current density JD is equal to I by A. So we can write dou D by dou T. So now you apply all these things into here. Therefore according to our concept. So what we stated at the beginning. So closed integral of H dot dl is equal to I, that is equal to J dot ds. So here J denotes conduction current plus displacement current. So Jc plus Jd. So the expression for Jc we derived sigma into E, Jd dou E by dou T. Therefore closed integral of H dot dl equal to surface integral of sigma into E plus epsilon into dou E by dou T into dt. Therefore H dot dl is equal to this value. So this is the integral form of Maxwell's equation from Ampere's circuit law. So now coming to this, therefore H dot dl. So by applying Stokes theorem, we can write del cross H dot dl. So from comparing these two equations, we can write double integral of del cross H into ds equal to, so left hand side both the equation equal, so make it right hand side also equal to, therefore del cross H is equal to J plus dou D by dou T. So finally we can write J is equal to sigma into E, dou T by dou T is equal to epsilon into dou E by dou T. So this is point form of Maxwell's equation. This is integral form of Maxwell's equation from Ampere's circuit law. So next we have to move to from Faraday's law, we have to derive the same Maxwell's equation. So Faraday's law states that the electromagnetic force induced in a circuit is equal to the rate of decrease of magnetic flux linking the circuit. So we can write V is equal to minus dou phi by dou t. Again dou phi by dou t. Phi value we can write surface B dot ds. So surface integral of B dot ds. Therefore V is equal to closed integral of E dot dl. So now both the things related V. So left hand side both the equation denotes voltage. Therefore make it right hand side equal. So E dot dl is equal to minus dou B by dou t surface integral of B dot dl. So we can write E dot dl is equal to minus mu into dou h by dou t. So this is the integral form of Maxwell's equation from Faraday's law. So now apply Stokes theorem. E dot dl we can write surface integral of del cross E into ds. So now comparing these two equations we can write right hand side is equal del cross E is equal to minus dou B by dou t. Therefore del cross E is equal to minus dou B by dou t. This is point form of Maxwell's equation. We can write B is equal to mu into h. We'll get minus mu into dou I by dou h by dou t. This is the point form or differential form. Both are same. So you can either may call it as point form or differential form. So this is the differential form of Maxwell's equation from Faraday's law. Third one, electric Gauss law. So Gauss law we know the total flux emerging through any closed surface is equal to total charge enclosed by the surface. So the total flux emerging you can write d dot ds equal to q. So again triple integral of rho v into dv is equal to q. So that you can write surface integral of d dot ds equal to triple integral v into rho v dot dv. This is the integral form of Maxwell's equation in electric Gauss law. So by applying divergence theorem in the left hand side equation we can write surface integral of d dot ds equal to volume integral of del dot d into dv. Now equate the right hand side of these two equation, you will get del dot d is equal to rho. This is the point form of Maxwell's equation from electric Gauss law. Next from magnetic Gauss law. So according to magnetic Gauss law, the total magnetic flux through any closed surface is equal to 0. So phi is equal to 0. So you can write B dot ds equal to 0. So now applying divergence theorem, B dot ds we can write volume integral of del dot B into dV. So now comparing these two equations, volume integral del dot B is equal to 0. That means del dot B is equal to 0. This is differential form of equation. Now summarizing all the equations. So first equations from Ampere's law, that is line integral of h dot dl equal to surface integral of j dot dou d by dou t into ds. So this is conduction current density, this is displacement current density. So in differential form it will be del cross h is equal to j plus dou d by dou t. Second from Faraday's law, line integral of E dot dl is equal to minus surface integral of dou b by dou t into ds. In point form del cross E is equal to minus dou b by dou t. Again from electric Gauss law, surface integral of d dot ds equal to volume integral of rho v into dv. So that is equal to del dot d into rho v. Similarly from magnetic Gauss law, surface integral of b dot ds equal to 0, del dot b is equal to 0. So this you have to summarize from all the equations for Maxwell's equation from the fundamentals law. Thank you.